welcome to the deep dive. We are jumping straight into the technical report for Tongyi DeepResearch. This is a really significant new release from the Tongyi DeepResearch team over at Alibaba Group. Okay, for those of you needing the quick version, here's the 1-minute hook. What we're looking at is a new kind of agentic large language model. It's specifically built for these really long, complex research tasks, deep information seeking. Now, what makes it stand out immediately? Well, first, efficiency. It's got 30.5 billion parameters total, but, and this is the kicker, it only activates 3.3 billion per token. That's a massive difference in compute needed. Second, the performance. It's hitting state-of-the-art among open source systems. We're talking benchmarks like Humanity's Last Exam and BrowseConf.
Yeah, and the way they got there, the sort of secret sauce, is this novel end-to-end training framework. It combines what they call agentic mid-training and agentic post-training. And maybe the most interesting part, it's all powered by a highly scalable, fully automatic synthetic data pipeline. Zero human annotation needed, even for these complex tasks.
Zero human annotation. That's the phrase that really jumps out, right? For anyone working in AI, particularly ML engineers and researchers, this is potentially huge for open source research agents. And that efficiency point, 3.3 billion active parameters, that really changes the game economically for deploying these kinds of tools.
Okay, so let's unpack how they actually did this.
Right. So first, maybe let's define what they mean by deep research capability.
Yeah.
It's not just finding one answer.
No.
It's about the agent autonomously conducting multi-step reasoning, searching across the internet, pulling information together for really complex questions, stuff that, might take a human expert hours.
Several hours, yeah.
And the agent aims to do it in tens of minutes.
And there's a clear mission here, too, isn't there? They seem to be pushing for more openness.
Definitely. The team explicitly states they want to open the era of open source AI researchers, which is a direct contrast to most of the big players right now. OpenAI, Google with Gemini, Grok. Those advanced research systems are typically closed source. You don't see the inner workings. So Tongyi is putting their method out there. What's the underlying architecture look like? Is it something totally new?
Actually, the core is surprisingly standard. It's based on the vanilla React framework.
Okay, thought and action.
Exactly. It synergizes the thought, which is the reasoning trace, and the action, which is using the tools. They kept the foundation simple, which is often a smart move in AI. Scale the simple idea rather than over-engineer complexity.
Right, rely on the data and the training. But simplicity at the core often runs into scaling problems. How do they handle the big one, context length, for these long research tasks?
Ah, yes. Context management. That's where they introduce something really interesting. It's to handle that finite context length problem, which always limits how deep an agent can explore.
So what's their approach?
They call it Markovian state reconstruction. It's a clever way to handle memory, instead of trying to cram the entire history of thoughts and actions into the context.
Which would overflow immediately on a long task.
Right. They condition the agent only on the essentials for the current step. That means the current question it's trying to answer, Q, an evolving summary report of what it's found so far.
Like a running brief.
Exactly.
Yeah.
A running brief. And then just the immediate last interaction, the last action taken, and the observation received.
Okay, so it's constantly updating a summary and focusing on the immediate next step based on that summary and the very last thing that happened. That avoids the need to remember step 1 when you're on step 50.
Precisely. It maintains focus, prevents context overflow, and allows for, in theory, arbitrarily deep exploration because the state representation remains compact.
That makes sense. So that's how it thinks and manages information over time. What about acting? What tools does it actually have to work with?
It's got a pretty solid toolkit for research. 5 main tools. There's standard web search, visit for going to specific URLs and extracting info, a Python interpreter for computation or data manipulation.
Always useful.
Google Scholar, specifically targeting academic papers.
Crucial for deep research.
And finally, a file parser, so it can handle documents, maybe PDFs or other formats it finds. Covers the basis for online information discovery.
Okay, comprehensive toolkit, smart context management. Now, let's get into the training itself. You mentioned this 2-stage framework with mid-training. That sounds like the core innovation.
It really is. Most agent training focuses heavily on the post-training phase. Supervised fine-tuning, SFT, or reinforcement learning RL on top of a base model.
Right.
Tongyi adds this critical bridge step, agentic mid-training, or agentic continual pre-training, CPT as they call it.
So why is that necessary? Why not just fine-tune a good base LLM like Gwen 3?
Because those general foundation models, even powerful ones like the Qwen 330B base they used, are trained on text. They're great at language, but they don't inherently know how to be agents. They lack that agentic inductive bias.
The instinct for tool use and planning.
Exactly. The mid-training is like taking that brilliant language model and specifically teaching it the process of research, how to plan, how to reason about which tool to use when, how to integrate the results. It bridges the gap between text prediction and goal-directed action.
Got it. It's like basic training for agents before the advanced stuff. And they do the CPT in stages with expanding context.
Correct. 2 stages. First, with a 32K context window, then they expand it to 128K. This isn't just about fitting more data. It's designed to specifically teach the model how to handle the long sequences of actions and observations that occur in deep research tasks. It forces it to learn long-range dependencies and agent behavior.
And the data for this mid-training stage? Also synthetic?
Fully automated synthesis again. They generate data covering the whole cycle, synthesizing research questions, planning actions, reasoning steps, and even explicitly modeling the decision-making as an action.
Interesting. Okay, so that sets the foundation. Then comes phase 2, agentic post-training. And you mentioned a superhuman data synthesis engine here.
Yeah, this part is pretty cool. They have this automated pipeline, shown in Figure 4 of the paper, that generates complex question-answering pairs without needing any human examples.
How does it work? How do they guarantee quality or difficulty?
It starts by building a knowledge graph. Then it samples subgraphs to create initial QA pairs. But the clever part is the uncertainty injection. They systematically increase the difficulty.
How do you inject uncertainty automatically?
For instance, they might merge entities in the knowledge graph that have similar attributes, creating ambiguity, or introduce conflicting information. This forces the agent to learn to disentangle subtle differences, resolve conflicts, and reason across multiple, potentially noisy sources.
So they're not just making questions longer. They're making the underlying reasoning problem harder, more ambiguous, like real research.
Exactly. They claim this lets them scale up the generation of PhD-level questions, requiring deep expertise and multi-source reasoning all automatically. That scalability for complex data is a huge bottleneck they seem to have tackled.
Wow. Okay. And this post-training phase still starts with supervised fine-tuning, SFT.
Yes, SFT provides the cold start. They use high-quality trajectories filtered from their synthetic data to give the agent a solid initial policy, a baseline behavior.
And they use a mixed approach here too, right? Combining different modes.
That's right. A mixed training paradigm. They blend samples trained in the standard React mode, step-by-step thought, action, observation, with samples trained using that context management mode we talked about earlier.
Ah, so they're explicitly training the agent, not just to act step-by-step, but also how to summarize its findings into those concise reports, right from the SFT stage.
Precisely. It reinforces state analysis and strategic summarization alongside the basic action policy. Makes the agent better at managing its own understanding during long tasks.
Okay, that makes sense. Which leads us to the reinforcement learning phase. What's the setup there?
They use a tailored GRPO algorithm generalized policy optimization. It's a type of trusted region method, generally known for being pretty stable in RL. And they combine it with a strict on-policy approach.
And the reward signal. Is it complex?
Surprisingly simple. It's a pure binary reward.
Yeah.
1, if the final answer is correct, 0 if it's wrong. They call it RLVR reward learning from voted results, likely using some consensus or ground truth check.
Just 0 or 1. So the paper makes a point that success here hinges more on data quality and environment stability than the specific RL algorithm. Why is environment stability such a big deal if the reward is that simple?
Because the agent is interacting with the real internet. Think about using web search APIs or Google Scholar.
They can be slow, they can fail, they can return weird results.
Exactly. Latency, failures, just general volatility. If your environment is unreliable, your training data, the agent's experience trajectories gets corrupted. The agent might fail not because its reasoning was bad, but because the Sleech API timed out.
And you can't tell the difference easily during training. Just looks like a failed trajectory. Makes debugging impossible.
Totally. So their solution, and it seems like a major engineering effort, is the unified sandbox.
Okay, tell us about the sandbox.
It's essentially a layer that sits between the agent and all the external tools. It manages all those API calls, search, visit, Python, everything. And crucially, it implements fault tolerance.
Like what?
Things like concurrency control, so it doesn't overload APIs, aggressive caching of results, automatic timeouts and retries if a tool fails, and graceful degradation if something is partially unavailable.
So it shields the agent. It takes the messy, stochastic real world and presents a clean, deterministic, reliable interface to the agent for tool use.
That's the idea. It insulates the learning loop from all that real-world randomness. This stability is probably essential for making the RL phase actually converge, especially with just a O1 reward over potentially thousands of steps.
That sounds like a huge piece of practical engineering needed to make Agent RL work reliably. Did they do anything else for stability or iteration speed?
Yes, they also built a simulated wiki environment. They call it their wind tunnel laboratory.
I like that.
It lets them iterate really quickly and cheaply on policy ideas, test hypotheses, find optimal strategies in a controlled setting before deploying them to the real sandbox environment, which involves expensive API calls and real web interaction. Very pragmatic.
Makes sense. Test in the simulator, validate in the stable sandbox.
Yeah.
Now, they found something interesting about context length during this RL phase, didn't they? Something almost counterintuitive.
Yeah, this was fascinating. They trained models with different context limits, say 32K versus 64K, but used a curriculum potentially designed for the larger context.
So what happened when the 32K model hit problems that really needed more than 32K context to solve optimally?
Well, it was forced to fail on those trajectories, right? It couldn't fit the optimal longer solution, so it received a zero reward. But the interesting effect was that this implicit pressure, this zero reward penalty for being too verbose, it actually forced the 32K model to discover shorter, more concise, more potent action sequences that did fit within its context limit. Over time, its average response length went down, and its efficiency seemingly went up.
That is wild. Constraint leading to optimization. The model learned to be more efficient because the training setup punished inefficiency, even implicitly. That's a really cool finding, especially for teams without massive context windows.
Definitely a surprising form of optimization through curriculum design. Okay, so all this engineering, the mid-training, the sandbox, did it pay off? Let's look at the results.
Right. The headline is state-of-the-art among open source agents. And that efficiency factor, again, only 3.3 billion active parameters. How did it do in the benchmarks?
Pretty impressively. Looking at ABGI at 3, the average performance over 3 runs on humanities last exam, it scored 32.9. That's notably better than DeepSeek v3.1, which was around 29.8, and even reportedly better than a version of OpenAI's DeepResearch at 26.6.
Okay, so strong on that complex benchmark. What about others?
Good generalization, too. 72.2 on WebWalker QA, a very high 90.6 on Frames. Shows it's not just a one-trick pony. And the pass at 3 results, which measure if any of the 3 runs succeeded, were also strong, like 63.7 on BrowseCompCH, the Chinese version.
Solid performance. And then they introduced something called heavy mode. What's that about? Trying to squeeze out even more performance at test time.
Exactly. It's a way to leverage more compute during inference to potentially get better answers. It's basically an ensemble method, but done cleverly given their architecture.
How does it work? You can't just average the outputs of multiple agents easily if their reasoning paths are super long, right? Context limits again.
Right. So they lean on that context management capability again. Heavy mode runs in agents in parallel on the same problem. But instead of trying to combine their full, lengthy thought processes.
Each agent produces one of those compact summary reports, stuck.
Precisely. Each of the in-agents generates its final, concise summary report. Then a separate synthesis model takes these n-compact reports as input and synthesizes the final answer.
That's smart. They use the agent's trained ability to summarize as the key to making ensemble reasoning scale within context limits. Does it help?
It does. The results show substantial improvements using heavy mode. They achieved their best pass at 1 scores the probability of getting the answer right on the first try using this method. For example, 58.3% on BrowseComp and 58.1% on BrowseComp-ZH.
Okay, so wrapping up the technical side, the big picture seems to be Tongyi DeepResearch shows a clear path. Combine agentic mid-training, large-scale synthetic data with controlled difficulty, and crucially, a stabilized training environment.
And you can get highly competitive open source research agents
that are also computationally efficient. That 3.3 billion active parameter number is still stunning. It really validates this overall approach.
Yeah, it provides a strong blueprint, especially for reproducible research in this area. But, the team is also upfront about limitations.
What do they flag?
Well, even 128K context, while large, might still not be enough for the absolute most complex long horizon research tasks. There's always a push for more context or better ways to manage it.
And the generality aspect.
Right. They mentioned the ongoing challenge of moving from agents that are good at specific domains, like web research, to truly general-purpose agents that can reason and act effectively across many different fields and task types fluidly. That's still a major frontier.
Definitely. And that push towards general agency ties into the final thought the report leaves us with. They note that model training increasingly converges with agent training. So for you listening, what does that convergence mean? If future LLMs are trained not just on text, but inherently learn tool use and interaction as part of their core training, how does that change how we even define a foundation model?
Is pre-training on static text alone becoming obsolete if the model doesn't learn how to act in an environment from the start?
That's the provocative question. Does intelligence now require agency to be baked in much earlier? Something to think about.